December 18, 1944. The Ardennes forest is silent under fresh snow. American infantry dig shallow positions between frozen trees, breath turning to fog in the dark. Somewhere beyond the tree line, German units move forward with confidence. They have done this before. Artillery fire means little if it explodes too early, or too late. Then it happens. A dull thump echoes from behind the American lines. An artillery shell rises, unseen, into the gray winter air. It does not strike the ground. It does not wait for a timer to run out. It explodes above the trees. Steel fragments rain downward in a perfect sphere. Not into earth, but into men. Helmets shatter. Formations collapse. Survivors scatter in confusion, convinced they have walked into a new kind of ambush. German reports later describe it as impossible. Shells that seem to think. Explosions that knew exactly when to happen. There is no new radar station here. No observer calling corrections. No visible guidance at all. Yet the shells are finding their moment. And behind this sudden shift on the battlefield lies a secret so tightly guarded that even many American soldiers using it had no idea how it worked, only that the war had just changed. To understand how this moment became possible, we must step back to a world where radar alone was no longer enough. By the time the United States entered World War II in December 1941, radar was already being hailed as a miracle of modern warfare. It could see aircraft beyond the horizon. It could warn cities and fleets before bombs ever fell. Britain had survived the Battle of Britain largely because radar gave it time. But radar had a fatal limitation. It could see the enemy. It could not stop them. Across Europe and the Pacific, anti-aircraft gunners faced the same brutal reality. Knowing where an aircraft was did not guarantee it could be hit. Hitting a fast-moving target in 3 dimensions, speed, altitude, direction, remained one of the hardest problems in warfare. Before 1942, anti-aircraft fire relied on 2 methods. The first was impact fuses. Shells exploded only if they struck the aircraft directly. Against fast bombers, this was almost useless. A direct hit was rare. Most shells passed close, sometimes within meters, yet did nothing. The second method was the time fuse. Gunners calculated how long a shell should fly before detonating. A mechanical timer was set before firing. If calculations were perfect, the shell might explode near the aircraft. They almost never were. Aircraft speeds changed. Altitudes varied. Wind altered trajectories. Even small errors meant the shell detonated too early, too late, or not at all. Entire barges could fill the sky with explosions and still fail to bring down a single plane. During the German Blitz of Britain in 1940 and 1941, this inefficiency was terrifyingly clear. British studies showed that thousands of shells were required for a single confirmed kill. Cities burned while guns thundered uselessly. Radar provided warning, but not precision. By 1942, the situation grew worse. Aircraft were flying faster. Flying higher. Maneuvering unpredictably. Dive bombers in the Pacific attacked ships at low altitude and extreme angles. Kamikaze tactics would soon push the problem to its absolute limit. The United States Navy understood what this meant. A single aircraft that slipped through defenses could cripple or sink a capital ship. Battleships and carriers carried hundreds of anti-aircraft guns, yet success still depended on probability, not certainty. The Army faced a different but equally dangerous challenge. Artillery was the backbone of ground warfare. But conventional shells exploded on impact with the ground, sending fragments outward horizontally. Against infantry in trenches, foxholes, or forests, this reduced lethality. Soldiers could survive by staying low. To kill effectively, shells needed to explode above the ground, where fragments would rain downward. Time fuses were again the answer in theory. And again, they failed in practice. This was not a lack of effort. By 1941, both Britain and the United States had invested heavily in fire control computers, predictors, and radar-guided aiming systems. These devices calculated trajectories faster than human crews ever could. But every system still relied on one final assumption, that a mechanical timer could guess the exact moment of detonation. It was an assumption that no longer held. As losses mounted, a radical idea resurfaced, one that had been discussed, dismissed, and revived repeatedly since the First World War. What if the shell didn't need to be told when to explode? What if it could decide for itself? The concept bordered on absurd. An artillery shell experienced tens of thousands of Gs during firing. It spun violently. It had seconds to live. There was barely room for explosive filler, let alone intelligence. And yet, by late 1940, a small group of scientists began to argue that recent advances in electronics had changed the rules. Miniature vacuum tubes were shrinking. Radio circuits were becoming more reliable. If a transmitter and receiver could be made small enough, and strong enough, they might fit inside a shell. If that shell could emit a radio signal, and if that signal could bounce off a nearby aircraft or the ground, then the shell would not need a timer at all. It would explode at the precise moment it mattered most. The idea was revolutionary. It was also incredibly dangerous. A shell that exploded at the wrong moment, inside a gun barrel, or over friendly troops, would be catastrophic. The margin for error was zero. Still, as the war expanded and conventional solutions failed, the United States made a decision that would alter the course of the conflict. The problem was no longer whether such a weapon should be built. It was whether it could be built in time, and kept secret long enough to matter. That question would soon pull America's scientific community into one of the most intense and hidden engineering efforts of the entire war. Turning theory into a working weapon required more than imagination. It required a complete rethinking of what an artillery shell could survive. In 1940, the U.S. Navy quietly asked a simple question that had no simple answer: could a radio operate after being fired from a gun? When an artillery piece fired, acceleration exceeded 20,000 Gs. Any fragile component shattered instantly. Vacuum tubes cracked. Solder joints failed. Batteries collapsed under stress. Even if electronics survived launch, they had to function while spinning thousands of times per minute. To solve this, the Navy turned to civilian science. In August 1940, the Johns Hopkins University Applied Physics Laboratory was created for a single purpose: develop a fuse that did not rely on time or impact. The project was classified from its first day. Only a small number of officers even knew what the laboratory was working on. The problem list was brutal. First, miniaturization. The entire system, transmitter, receiver, power source, detonator, had to fit inside a shell's nose. Second, durability. Components had to survive launch, flight, and violent spin without losing calibration. Third, power. Conventional batteries were too fragile. Engineers designed liquid-filled batteries that activated only after firing, using centrifugal force to mix electrolytes mid-flight. Fourth, false triggers. Rain. Trees. Birds. Terrain reflections. The fuse had to ignore everything except the intended target. Early prototypes failed spectacularly. Some exploded too early. Others failed to detonate at all. A few detonated randomly, reinforcing fears that the entire concept was too dangerous for battlefield use. Yet incremental progress continued. By late 1941, engineers achieved a breakthrough. The fuse emitted a continuous radio wave. When the shell approached a target, the reflected signal interfered with the transmitted wave, creating a measurable change in frequency. That change triggered the detonator. It was simple in theory. It was genius in execution. The system required no external guidance. No radar link. No operator input. The shell did not see the target, it sensed proximity. This simplicity made it nearly impossible to jam. There was no signal for the enemy to detect in time. The fuse operated autonomously, in silence, for only seconds. Secrecy now became the dominant concern. If a single unexploded shell fell into enemy hands, the entire advantage could vanish. German scientists were among the best in the world. Given time, they might replicate the concept. As a result, usage was tightly restricted. The Navy was allowed to use the fuse first, but only over water. If a shell failed to explode, it would sink, unrecoverable. Ground use in Europe was forbidden. Testing at sea began in 1942. Results were immediate and undeniable. Anti-aircraft kill rates increased dramatically. Ships reported aircraft being destroyed without direct hits. Explosions occurred at optimal distances, close enough to shred wings, engines, and pilots. Still, authorization expanded slowly. Every deployment required approval. Every shell was tracked. Crews were warned never to fire over land. The weapon's existence remained classified even as it was used in combat. By 1943, the fuse was mass-produced in the millions. American industry solved problems that once seemed impossible. Reliability reached levels acceptable for war. But its greatest potential remained locked away. On land, against massed infantry, the fuse promised something unprecedented, artillery that did not merely suppress, but devastate. That moment would come only when the war itself reached a breaking point. Until then, the weapon waited. Quietly. Silently. Packed inside steel shells that looked no different from any other. The men who fired them were often told nothing, only that these shells were special, and that they must be used exactly as ordered. Soon, circumstances would remove all hesitation. And when that happened, the world would see what happened when a shell no longer needed instructions. It only needed something nearby. For American gunners, war had always been an exercise in uncertainty. They loaded shells. They adjusted elevation. They trusted calculations scribbled in cold, wet notebooks. And then they waited to see if anything happened. Most of the time, nothing did. With the new fuses, something changed, not in the sky, but in the men themselves. Crews noticed it immediately. They fired fewer rounds. They watched aircraft break apart after near misses that would have meant nothing before. Artillery units saw infantry attacks collapse after a single barrage. There was no celebration. Only quiet realization. The weapon removed guesswork. It replaced hope with expectation. Veterans later recalled how strange it felt. The shell no longer needed perfect aim. It only needed proximity. Gunners stopped trying to hit targets and began trying to approach them. In forests and open fields, explosions came from above, not below. Fragment patterns shifted. Soldiers who once survived by hugging the ground found that instinct no longer protected them. For the first time, artillery behaved as infantry had always feared it would. Technological angle, how the fuse worked. Despite myths that followed the war, the proximity fuse was not magic. It was elegant physics. Inside the shell's nose sat a miniature radio transmitter and receiver. The transmitter emitted a continuous signal. As the shell flew, that signal radiated outward. When the shell neared an object, an aircraft, a vehicle, or the ground, the signal reflected back. The returning wave interfered with the outgoing wave, producing a frequency shift. That shift triggered the detonator. No timers. No commands. No external systems. The fuse required no radar network. It operated entirely on its own, for mere seconds, before destroying itself. This autonomy made it nearly impossible to counter. Jamming required advanced detection. Detection required time. The fuse allowed neither. German attempts to understand the phenomenon were slow. Reports spoke of shells detonating as if guided. But without intact examples, analysis stalled. The device's greatest strength was also its invisibility. It left nothing behind to study. Enemy angle, confusion and misinterpretation. German and Japanese forces experienced the weapon before they understood it. In Europe, German infantry advancing through forests during the winter of 1944 reported artillery bursts above tree level. Casualties were severe. Survivors believed they were facing new airburst tactics or improved observation. Some assumed radar-directed artillery had reached the front lines. Others believed American gunners had finally perfected timing methods. Few suspected that the shell itself had become the decision-maker. In the Pacific, Japanese pilots encountered something worse. Aircraft approaching U.S. ships were destroyed at distances previously considered safe. Near misses turned lethal. Dive bombers disintegrated before reaching release altitude. Pilots adjusted tactics. They flew lower. They came faster. Losses increased anyway. Post-war analysis revealed the truth. Neither Axis power had deployed a comparable system during the war. Research existed. Concepts were known. But none had solved the engineering challenge in time. By the time intelligence services realized what they were facing, the opportunity had passed. The weapon's secrecy held. Its effects multiplied. And pressure mounted inside Allied command structures to use it everywhere, not just where loss of secrecy could be controlled. That decision, once unthinkable, was about to be made. For senior Allied commanders, the proximity fuse represented both opportunity and risk. The Navy had embraced it first. Over open water, secrecy could be preserved. Unexploded shells vanished beneath the surface. If the fuse failed, it failed safely. The Army situation was different. Land warfare left evidence behind. A single dud shell in German hands could undo years of research. Commanders feared that if the enemy reverse-engineered the device, the advantage would disappear overnight. As a result, authorization was restrictive. Units received shells with minimal explanation. Orders were precise. Usage conditions were narrow. Officers were warned of consequences if procedures were ignored. But by late 1944, circumstances overwhelmed caution. German forces launched a massive counteroffensive through the Ardennes, the largest surprise attack on the Western Front since 1940. Weather grounded Allied aircraft. Roads clogged with refugees and retreating units. American artillery became the primary line of defense. Requests for proximity fuses surged. Commanders faced a choice: preserve secrecy, or preserve the front. They chose the front. Strategic angle, changing the math of war. Once approved for ground use, the fuse altered battlefield mathematics instantly. Traditional artillery required massed fire to achieve effect. Proximity-fused shells required precision in placement, not timing. Fewer rounds produced greater casualties. Smaller units gained disproportionate stopping power. Defensive positions became killing zones. In the Ardennes, forests that once absorbed explosions now amplified them. Airbursts sprayed fragments downward, bypassing cover. German assault formations broke apart under fire that seemed to anticipate movement. This was not a new doctrine. No new manuals were written. The same guns fired the same shells. Only the fuse had changed. The result was a quiet revolution in lethality. Moral angle, an invisible threshold. The proximity fuse raised no immediate ethical debates during the war. There were no protests. No public discussions. Few even knew it existed. But its effect was unmistakable. It did not merely improve weapons, it optimized them against human vulnerability. It exploited the fact that soldiers looked up. That they ran. That they sought cover where fragments now fell most densely. The weapon killed efficiently. Impersonally. Unlike bombs or chemical agents, it left no signature beyond destruction. No lingering contamination. No new category of suffering. Yet those who witnessed its effects understood something fundamental had shifted. The battlefield no longer required a human decision at the moment of impact. That decision had been embedded in metal and circuitry. The fuse did not hate. It did not hesitate. It simply functioned. As winter deepened and the Battle of the Bulge reached its most desperate phase, the full implications of that shift were about to be revealed. The Germans were advancing. The skies were clearing. And American artillery was ready. December 1944. The Ardennes offensive reaches its peak. German forces push westward through narrow roads and dense forests, aiming to split Allied lines and seize Antwerp. Infantry advances are rapid. Armor follows wherever fuel allows. The weather, low clouds, snow, freezing fog, has neutralized Allied air power. For American commanders, artillery becomes the final barrier. Guns are positioned behind ridgelines and villages. Forward observers work from frozen foxholes and shattered buildings. Fire missions come constantly, often without clear visibility of the enemy. This is where the proximity fuse enters fully. For the first time on land, artillery shells are ordered to detonate above ground, deliberately, systematically, across entire sectors. The effect is immediate. German infantry advancing through woods near Elsenborn and Bastogne encounter explosions above tree height. Branches shatter. Shrapnel rains downward in lethal patterns. Units trained to survive shelling by staying low find no protection. Entire platoons are broken before reaching contact. Reports from American units describe something unprecedented, German attacks halting under artillery fire alone. Not slowed. Not delayed. Stopped. At Bastogne, where the 101st Airborne Division is surrounded, artillery fires with proximity fuses become a defensive shield. German assault formations attempting night advances are shredded before reaching U.S. lines. Weather clears briefly. Aircraft return. But it is artillery, silent, unseen, that carries the heaviest burden. German after-action reports struggle to explain losses. Some officers believe Americans have perfected airburst timing. Others suspect new radar-linked systems. None identify the true cause. The secrecy holds. Meanwhile, American gunners notice something else. They are firing fewer shells. Fire missions that once required hundreds of rounds now require dozens. Ammunition stocks last longer. Guns overheat less. Crews move faster between targets. The tempo of defense accelerates. As the weeks pass, the German offensive slows, not only from fuel shortages and resistance, but from attrition inflicted by artillery that no longer wastes its power. By early January 1945, momentum has shifted. The Ardennes counteroffensive falters. American commanders credit many factors: logistics, leadership, resilience, but artillery reports reveal a quieter truth. Proximity-fused shells have multiplied defensive firepower beyond anything previously possible. One artillery officer later summarized it simply. "We finally had shells that did what we always wanted them to do." The turning point is not marked by a single explosion or order. It emerges gradually, as German units withdraw, regroup, and fail to advance again. But while Europe feels the fuse's impact on land, another theater is experiencing it in a different, equally decisive way. Across the Pacific, a threat is rising that will test American defenses to their limit. And once again, the proximity fuse will meet the moment. By late 1944, the war in the Pacific has entered a brutal phase. Japanese naval aviation, once dominant, is largely destroyed. Fuel shortages cripple training. Experienced pilots are gone. In their place emerges a tactic born of desperation. Kamikaze attacks. Aircraft packed with explosives dive directly into American ships. Speed, low altitude, and unpredictability make them extremely difficult targets. Even damaged planes remain lethal until the moment of impact. For U.S. Navy commanders, this is the worst possible scenario. Radar can see the aircraft coming. Fire control computers can calculate trajectories. But unless an aircraft is physically destroyed, it remains a threat. Here, the proximity fuse proves decisive. Mounted in 5-inch naval guns and smaller anti-aircraft weapons, the fuse transforms defensive fire. Shells no longer need direct hits. Near passes become lethal. Explosions blossom in mid-air around diving aircraft. Wings tear off. Engines disintegrate. Pilots are killed instantly. Statistical reports tell the story clearly. Anti-aircraft effectiveness increases by factors, not percentages. Ships record multiple kills from single engagements that previously would have overwhelmed defenses. At Okinawa, one of the most intense kamikaze battles of the war, proximity-fused shells become standard. Losses are still severe, but without the fuse, they would have been catastrophic. Japanese pilots describe sudden explosions they cannot evade. Approach angles that once worked no longer guarantee success. The sky itself seems hostile. Again, the weapon leaves no evidence behind. No wreckage reveals its secret. No radio signal warns of its presence. No countermeasure emerges in time. By mid-1945, the proximity fuse is everywhere the United States fights. It protects ships. It defends infantry. It amplifies artillery. And yet, it remains unknown to the public. As the war approaches its final months, Allied victory becomes inevitable. The Axis powers collapse under pressure from overwhelming force, logistics, and technology. Among those technologies, the proximity fuse stands apart. It does not change strategy. It does not alter grand plans. It simply ensures that when a weapon is fired, it works as intended. When Germany surrenders in May 1945, and Japan follows in August, the fuse has done its work quietly, without ceremonies or headlines. Its true impact will only become clear afterward, when historians, generals, and scientists begin to assess what truly mattered. And when they do, they will place this small device among the most important tools of the war. When the fighting stopped, analysts began measuring what the proximity fuse had changed. The numbers were stark. Before its introduction, anti-aircraft artillery required thousands of rounds per aircraft destroyed. With proximity fuses, that number dropped dramatically. In some naval engagements, effectiveness increased by as much as 5 times. Artillery units reported similar gains against ground targets. This was not merely efficiency. It was a fundamental shift in how firepower translated into results. Logistics officers noticed it first. Ammunition consumption fell. Guns required less maintenance. Units could sustain defensive fire longer without resupply. In prolonged engagements, this mattered as much as raw firepower. German post-war interrogations revealed the other side of the equation. Officers described artillery that detonated with unnatural precision. Infantry commanders noted losses that could not be explained by observed gun numbers alone. No effective countermeasure had been developed. The reason was simple. The Axis powers never acquired an intact fuse during the war. Secrecy had worked. Restrictions on land use were lifted only when necessary. Naval use ensured failures vanished underwater. Even after ground deployment, the fuse's short lifespan and reliability meant few unexploded examples existed to recover. German scientists, reviewing captured Allied documents after the war, admitted that the concept had been theorized, but not solved. Miniaturization, power supply, and reliability had proven insurmountable under wartime conditions. The fuse had arrived too late for imitation. For the Allies, its success reshaped doctrine quietly. Post-war artillery manuals incorporated airburst effects as standard practice. Anti-aircraft design shifted permanently toward proximity detonation systems. Mechanical time fuses were never again trusted as the primary solution. Yet during the war itself, the fuse remained almost invisible. No victory parades mentioned it. No public announcements celebrated it. Few soldiers even knew its name. The weapon did not symbolize triumph. It simply delivered it. As reports circulated through military institutions, comparisons emerged. Radar had warned. The atomic bomb had ended the war abruptly. The proximity fuse had ensured countless battles were won before either could matter. Its impact was cumulative, not dramatic. And that made it harder to see, until the war was over. In the months after Japan's surrender, the secrecy surrounding the proximity fuse slowly dissolved. Technical reports were declassified in stages. Scientists who had worked in silence were finally allowed to speak. What emerged was not a single invention, but a system, science, industry, and warfare fused into one result. Military historians struggled to categorize it. It was not a weapon in the traditional sense. It was an enabler. Radar could detect. Guns could fire. But without effective detonation, neither guaranteed results. The fuse closed that gap. General George S. Patton later referred to it as one of the quiet tools that made American artillery dominant. British assessments echoed the view, noting that airburst artillery had become decisive in late war engagements. Scientific communities took note as well. The fuse demonstrated that extreme miniaturization was possible under combat conditions. It accelerated research into rugged electronics, autonomous systems, and solid-state replacements for fragile components. Cold War weapons would inherit its logic. Missile proximity sensors. Air defense intercept systems. Modern smart munitions. All trace conceptual lineage back to a shell that decided when to explode on its own. Radar, by contrast, evolved as an information tool. It guided decisions. It warned. It observed. The fuse acted. This distinction shaped post-war military philosophy. Detection without effect was no longer sufficient. Weapons had to close the loop, from sensing to action, within themselves. The proximity fuse was one of the first battlefield technologies to do exactly that. And yet, it remained absent from popular memory. There was no single battle that belonged to it alone. No iconic photograph. No defining explosion. Its legacy existed in reports, casualty figures, and quiet acknowledgments by those who understood how close many battles had been. The device had no monument. Only outcomes. As decades passed, historians increasingly ranked it among the most important technological contributions of the war, often alongside radar and nuclear weapons, sometimes above them in terms of immediate tactical impact. It did not end the war. But it shortened it. And it saved lives on one side by ending them more efficiently on the other. That uncomfortable truth sits at the center of its legacy. And it leads naturally to the final question, what this weapon ultimately meant. Not just for World War II. But for the future of warfare itself. War is often remembered through images of soldiers, machines, and leaders. But history is just as often decided by what cannot be seen. The proximity fuse had no roar of its own. No signature. No moment of reveal. It lived inside steel, functioned for seconds, and vanished in fire. Yet during those seconds, it changed everything. It removed hesitation from combat. It replaced probability with certainty. It shifted power from human timing to embedded judgment. For the first time, a weapon did not wait to be told when to act. It knew. This was not artificial intelligence. It was far simpler, and far more dangerous. A closed loop between detection and destruction, operating faster than any human could intervene. Modern warfare has followed that path ever since. Smart bombs. Autonomous defenses. Systems that sense, decide, and strike within moments. All of them echo a wartime decision made in secrecy, that effectiveness mattered more than explanation, and that technology could carry intent inside itself. Radar warned nations of danger. The atomic bomb ended the war in a flash. The proximity fuse quietly ensured that battles were decided long before headlines were written. Its story reminds us that history does not always turn on spectacle. Sometimes it turns on a small invention, hidden in plain sight, doing exactly what it was designed to do, again and again, until the outcome becomes inevitable. And when the war ended, the shells stopped flying. But the idea they carried did not. It is still with us. Embedded. Autonomous. Waiting for proximity.